Get started if we could. Thanks for joining us this afternoon. My name is Darren Sessions. I am the Chief Technology Officer for Avoxy. I'm an open source advocate, longtime Asterisk community member, former Digimite. I have an extensive background in architecting, building, and scaling communications platforms.
My name is Leif Madsen. I am Director of Engineering, Product Development at Avoxy. I'm also co-author of Asterisk, the Definitive Guide, and a former Asterisk consultant specializing in distributed call center solutions.
So our talk today is centered around using Docker to distribute Asterisk. So we're going to be touching on a lot of different topics related to containers that include Coriolis, Tectonic, Calico, SIPI, RTP proxy, networking strategies surrounding containers, and some interesting approaches to scaling container infrastructure for use with VoIP applications. So we've got a lot of ground to cover in a short amount of time. So in the interest of just making sure that we get through everything, if everyone could hold any questions until the very end, that'd be fantastic. So let's talk about Docker and containers. What is a Docker container? A Docker container wraps up software in a complete file system that contains everything it needs to run. That's code, runtime, system tools, system libraries, anything you can install on a traditional virtual machine or a dedicated server. This approach guarantees that the Docker container will always run the same regardless of the environment or hardware that it's running in. So how exactly do containers differ from traditional virtualization? Well, containers running on a single machine all share the same operating system kernel. So they start instantly, they make more efficient use of RAM. Images are constructed from layered file systems so they can share applications from each other and the underlying infrastructure while providing an added layer of protection for the application. So you can see in this diagram, traditional virtualization, each instance of the application contains the necessary binaries and libraries plus an entire guest operating system, which equates to gigabytes of used space, wasted host resources, and more importantly, from an operations perspective, additional moving parts, maintenance, and management requirements. Simply put, Docker allows you to package an entire application with all of its dependencies into a standardized unit for easy software deployment, version control, packaging, deployment, maintenance, and management.
So the root of a Docker container is the image. The image is built through a file usually named the Docker file. This Docker file is a text file that contains various basic commands that define how an image is built. So from that resulting image, containers can be instantiated. You can either build images locally using the Docker file via the Docker build command, or pull them down from an image registry onto the Docker host itself. So because of the layered file system, you can either start from a scratch image, meaning that you need to define all the base dependencies to construct the layers of the application. Although more often, you're going to start from another image and build your application on top of that. So in our case, we're going to go through a Docker file and just show how all that operates and how you can put that together. And that's going to be built on top of the CentOS 7 image for our Asterisk application. So here's the top part of our Docker file. The full contents of this Docker file is located in the Avoxy GitHub organization within the certified Asterisk repository. The link is at the top and it'll be on the next few slides here. This image is likely to change, but I think it provides a good base of how to construct a full-featured Asterisk image. So the first line here is a comment in the file that can be used to define something like a version. It's not read by the Docker build process. That's what the hash part is. It's just defining a comment. But it's always nice to provide some metadata for our DevOps folks. So here we have the from keyword defines what base image we're going to build our application on. So in this case, we're going to be applying layers to the CentOS image. In this case, it's version 7. So here we've set the maintainer. In this case, it's the Avoxy DevOps department. Lines starting with env are environment variables that can be used throughout the file in place of hard-coded text, effectively variables throughout the file. These environment lines can also be overridden at build time from the console. So next up here we have a run command, which defines commands that are going to be run during the build process. In this case, we're installing the development dependencies. At the end of this line here, we have $dev package list and run package list, and their values from our values contained from previously defined environment variable lines. Workdir sets the working directory that the following sets of commands will get run during the build of the image. It's essentially the equivalent of a CD or a change directory command on the Linux console. The add command can take a local file location or a remote URI file location and adds the file into the image during the build process. The file is available and basically put in during that build. So if you add the file locally and it is a compressed archive, it will automatically be extracted for you. Unfortunately, remote files don't have the auto extract functionality currently, so we're adding another run command here to explicitly extract the file. One point to note is that every run command results in a new layer image, so we'll discuss the implications of that in a second. This command is basically running some cleanup of our files, so we're removing some different directory here. Unfortunately, because of the way Docker build system works, this won't actually result in a smaller image. Every time you execute a run command, a new layer is added to the image and it's applied. So back when we added our development dependencies, then extracted our source code, compiled the source, etc., we're adding new layers to that build. Doing cleanup at this point doesn't result in that smaller image when you're building it locally. There are some tricks that you can do to actually flatten the image a little bit, and we've documented some of that in the Git repo. Additionally, it appears basically if you use hub.docker.com and have it perform the build for you, it'll actually, it does some compression and probably does similar commands, since the same image that results in a 1.3 gigabyte file on the local file system is only 487 megabytes when it's built through hub.docker.com. So here's at the end of the file, this is where we define what application to start with in the container. So first we set our workdir to user sbin, then our entry point is the Asterisk application itself. We pass flags to the application using the cmd command. We do this in a separate command so that we can override the default set of flags passed to the entry point. Entry point itself is actually a more difficult command to override from the console. It's not impossible, but it's generally assumed that that entry point is always what you're going to enter, and then you pass the flags in, and this is kind of the default set of flags. So for example, I wanted to pass in -VVVV, I could do that from the console as an override to those initial two flags. So next here, this is where we're building our image from the console. So this is a Docker build command. Do this from the local console using the Docker application, and we pass the argument build to the Docker application with the -t flag that defines the name of the build, and optionally the tag for the build, so which in this case is called latest. If you looked at the from CentOS:7, same kind of thing there. The last argument is the path to the Docker file, which in this case is the local directory represented by the period. The build then works its way through the steps. So the first two steps should be familiar to you, having just looked at our Docker file in the last few slides. So step 0 defines the from image that we're building on top of. Step 1 executes the maintainer command, et cetera, et cetera, et cetera. So there's a bunch of tools that exist in the Docker world. So these are a few that we found pretty useful recently. So there's Docker Compose, which defines and runs a multi-container application. So if I had a bunch of different containers that all needed to work together, such as Asterisk and a database, I could define that in a single Docker Compose and then run that command. It'll instantiate and link them all and stuff like that. Docker Hub, which I kind of mentioned, it's a hosted registry with triggered image building from GitHub commits. So that's how ours is actually set up. When we commit to the GitHub repo, it'll automatically update and build a new Docker image and publish it and make it available to anyone who's basically following that repository. Shipyard, which is built on top of Docker Swarm, provides a web interface for container management. And Prometheus, we started playing around with recently. It's a service and container monitoring system, and it also includes a time series database, which is similar to InfluxDB. You can actually utilize InfluxDB if you want with it, but it has its own built-in. And then here's a few links just for posterity after the fact. So here's just kind of a quick rundown of some useful commands for Docker. So there's the Docker build command that we showed. You can list the images on the system via Docker images, the Docker PS and Docker PS-A will show you a list of Docker containers. With PS, it just shows you running containers. -A shows you containers that are not currently running. You can pull down images with Docker pull, and if you want to see more information about how image was created, you can utilize Docker inspect. So one of the more interesting things that I've found recently is just an understanding of how volumes work with Docker. So in a traditional virtualization system, the OS, the storage, and the application are all deployed together. For Asterisk, typically you would have your Asterisk application, which here is designated in blue, or the top box, and your call recordings, your music on hold files, your prompts, things like that. That'd be deployed into storage, which is the middle or the orange box. And all of this sits on top of the operating system, which may or not be consistent across each of your virtualization deploys. You can utilize things like NFS and iSCSI and things like that to start abstracting your storage layer, of course, but typically you're going to write it locally first and do some post-processing, at least in the case of call recording. So in Docker, application containers contain the actual application and the dependencies to run that application, but their configuration that the application loads and the data they create are not stored within that container directly. So basically, where does the application store the information and load their configuration files? So they load them from volumes, which is a storage location for data. In Docker, data is separate from the application itself, stored in the volume. So here's kind of like a little overview. So when an application is instantiated, there's a volume option in that Docker file that you could use, and that causes a volume to be created at the same time as the application. The volume is then assigned a mount name that is referenced from the application as a directory. So for example, I could create a volume that mounts into the application at var_spool asterisk recordings. Recordings from that asterisk instance then writes to the volume. Beyond that, you can also use the -v flag when executing Docker run to create a volume and link it to the container. You could also specify a local directory on the Docker host itself to be mounted into the container. Any changes made in the directory on the Docker host are then reflected into the container linked to that storage volume. Additionally, you can sort of meld the volumes and the containers together. So for example, where do my sound prompts get loaded? I don't necessarily want to load the prompts onto every Docker host itself and then link the directory into the application, because I'm kind of back to the same issue of having those out-of-sync prompts across all my hosts. It's definitely better, but it's not per application instance. So instead, we can use something called a data volume container. These containers start up and then immediately exit, but they provide a volume that can be linked into the containers. So in this way, we can distribute our sound prompts as a data volume container with versions and a defined set of prompts across hosts. So we can easily update these to the latest version and do that across all hosts fairly easily. The one thing to just make note of is that all the application containers can share that same data volume container, so it's not a 1-per-1. So you end up with that on 1 per host, and everything actually shares that and utilizes that single instance of the sound prompts.
So I'm not going to go into a lot of detail, but I want to do a quick overview of two relatively new projects, and that is Coriolis and Tectonic. Coriolis is a powerful yet intentionally minimalistic Linux distribution that makes scaling Docker on large and varied infrastructure simple to manage. Coriolis incorporates services like etcd, which is used to store and distribute data to each of the hosts in a cluster, Fleet, which is a distributed init system, and Flannel, which provides overlay-based networking, and of course there are many other services as well. Tectonic is a container technology stack combining the Coriolis portfolio with Kubernetes, which is Google's open source project for managing containerized applications, or to put simply, Google's infrastructure for the common man. Kubernetes at its basic level is a system for managing containerized applications across a cluster of nodes. In many ways, Kubernetes was designed to address the disconnect between the way that modern clustered infrastructure is designed and some of the assumptions that most applications and services have made about their environments. While it's possible with most clustering software to make these types of scheduling decisions, operating at a level of individual services is not ideal. Applications comprised of different services should still be managed as a single application in most cases, and Kubernetes provides a layer over the infrastructure to allow for this type of management. Tectonic prepackages all of the components required to build Google-style infrastructure and adds additional features such as a management console for workflows and dashboards, an integrated registry to build and share Linux containers, and additional tools to automate deployment and customized rolling updates. When we talk about all these new and exciting technologies, we have to keep in mind that these technologies were built for web scale. And what is web scaling? Well, it just means that these projects were designed to scale web services specifically. When we talk about using applications outside of that realm, the dynamics of how these web scaling technologies are configured to support these non-web-based applications changes dramatically. And that is to say that it is virtually impossible to use Asterisk with any of these platforms out of the box in a production environment without a significant amount of work. So what does a pretty typical large deployment of Asterisk look like at the end of the day? In this diagram, we have Calico at the front end tying into SIPI, which is a BTB UA. We have RTP-proxy and, of course, Asterisk. And in this type of an environment, how do we scale Asterisk? The answer is simple, ARI. So ARI allows us to centralize the call handling logic, which in turn allows us to use a collective pool of cookie-cutter Asterisk servers or cloud instances, much like a Puppet and a Puppeteer. By abstracting and centralizing the call handling logic away from the Asterisk servers, we lower our management costs on a per server basis and radically enhance our infrastructure efficiency by allowing an Asterisk server to handle any call request. All this sounds great, but what then handles the call handling logic? Some folks use caching technology, databases, and various other methods to handle call control at scale. One potential solution would be to use a message bus to communicate with a pool of Asterisk servers. Such a message bus could then be tapped into by various other components to do things like providing APIs to dramatically simplify product development, providing customer-facing APIs, easing integration of new technologies and services, data storage backends, caching engines, billing, logging, or anything else that can be made to talk to the message bus. When we talk about scaling in Docker containers, networking is also a critically important consideration. Networking containers isn't as easy as you'd think. The problem Docker was initially conceived to solve was a problem with scaling web services, and to that end, Docker, Coriolis, and a lot of these really cool web scale projects present a lot of bias to solving web scale problems. The obvious problem for us is we're VoIP users. In this simplified diagram, you can see two servers running Docker represented by the larger cubes, with individual Docker instances within the larger cube. With web scale services, each Docker instance occupies an individual IP port on the host, where it can serve up content. These containers are then fronted by a load balancer, typically HA-proxy, potentially a hardware-based solution like F5 or something along those lines, which load balances the request coming in from the internet. The fundamental problem here is NAT. So insert CoreOS into the equation running Flannel, and things get a lot more interesting on the networking front. Flannel uses an overlay network that gives each container instance that's part of a specific overlay an IP address that can be used for container-to-container communication. It uses packet encapsulation to create this virtual overlay network that can span the whole cluster. Pretty cool. So we've gone over what CoreOS is and what Tectonic is, so let's talk about Calico for a minute or two. Calico provides simple, scalable, and secure virtual networking for Tectonic. Calico uses BGP to distribute routes for every Tectonic pod or container, which allows it to seamlessly integrate into your Tectonic cluster with existing data center infrastructure without the need for overlays. The result is networking with exceptional performance and scale, simple to deploy, diagnose, and operate. Calico is particularly suitable for large deployments on bare metal or in private clouds, where the performance and complexity costs of overlay networks can become very significant. And it can also be used in public clouds like AWS, GCE, DigitalOcean, and Rackspace, just to name a few.
So today we went over, a bunch of new technologies, including Docker, Docker-related projects, CoreOS, and Tectonic. We talked about networking issues surrounding the deployment of non-web applications in a web-biased world, and some of the things it takes to truly scale your system horizontally. So I think we actually have time for questions. But if we don't get a chance to answer all your questions, we'll be hanging around outside after the fact. Just a couple other presentations to note. Tomorrow in the morning, Douglas Smith is doing one that kind of takes from where this is a little further and gets in a little more nitty gritty. And Russell unfortunately did his talk before us, but as everything's being recorded, be sure to check that out after the fact. So, questions?
So Kubernetes is Google's platform. Tectonic is basically the CoreOS implementation of Kubernetes. So it applies CoreOS's full stack in addition to Kubernetes.
Yep.
So, are you using Flannel, or were you saying you're using Calico?
Calico.
So you probably are better off to answer this, but they're basically independent. Like they're different plugins for networking. So Docker basically has the ability to plug in different networking stacks. One of them's Flannel, one of them's Calico. We've been playing around with Calico lately.
So what about the port problem of having are you using all internal IPs, and then I guess your proxies?
Yeah. So.
And Brad, you're more than welcome to chime in if you want, but
He's our networking guy.
So yes, internally it's all private networking, and you can do that either with Flannel or with Calico.
What's better, traditionally?
It honestly depends on your use case. I think that we determined that for our use case, Flannel is better, and we have a lot more VPS pieces as well, so it makes more sense for us to deploy it. Flannel comes with CoreOS, so it's kind of a box. You put it on Flannel and still build it out with CoreOS and not have yet another thing to install. So I would say I think try both and see what works better for your use case, but the performance of Calico is exceptional. So I would.
Apologies for anyone who couldn't hear Brad, but the networking part is really like the magic in the box. So that's probably if you have like specific network questions, that's definitely going to be a let's hang out and chat for an hour kind of
For sure.
idea. Just so you know. Yeah. Sure.
As far as I know, how Asterisk works is every instance has the IP address of the endpoint. So when you have several Docker containers, and how do the endpoint know to which Asterisk container that you're
Yes. So if I'm understanding the question, basically, so you have many Asterisk containers. How do the endpoints know where to go? So basically, that's where Calico comes in. It's the distribution point. It's the part where it has the external IP. It's the thing where all your clients go to, and then really your container network is really hidden from the outside world. There's really no knowledge of that container network being outside. So your distribution of the calls from the proxy then gets distributed amongst your internal network, and that's why you need either an overlay network or something like Calico or something, so that you're removing that NAT aspect, because by default Docker is going to be trying to utilize NAT for the containers, which works great when you're running Apache or Nginx or something, but with Asterisk you want to avoid that. So you create a more traditional network kind of in the back end for your containers. So then your Calico basically distributes it much like as if it was a virtualized network, but they're containers. And then that's why you abstract the actual logic outside of Asterisk itself into your applications, and then it communicates via ARI, so that you've removed that set of logic. So you actually have almost two layers of containers. You have your application logic and you have your media logic.
And Flannel is more geared towards, obviously, overlay networks. And so with CoreOS, basically you assign CoreOS etcd a /16 network, and it breaks that up into /24 networks. And so an overlay could be, an Asterisk container and then potentially something else off to the side. only talking within that overlay network and never bridging to whatever physical connectivity exists on the host or external of the host.
One last question.
Oh, yeah, we,
Question on the Docker file that we have.
yeah.
We have one in Docker already.
Yeah.
So is it possible to select to pick the application that you need? Let's say I need to find the voicemail IVR. Can you choose the ones that I want?
Yeah, so the way we've been doing that is I've been building kind of everything. So the question is, how do I basically choose and pick what modules are within that container, because it's already been pre-built for me, much like an RPM kind of. So the way we're doing that is use modules.conf with autoload equals no, and then just do a load list for each of the containers. Everything's already pre-compiled in there, and then you just load what you need into memory based on that modules.conf.
Now, so when you're deploying the cluster, are you typically using like Calico to front the SIP, and then like RT-proxy so you don't have to worry about the back issue with the media being out?
Well, so
Yeah.
there's Calico, SIPI, RTP proxy, and Asterisk. And so RTP proxy and SIPI are at the edge. Calico is obviously at the edge, so to speak, as well. The reason that SIPI is part of that equation is the B2B UA functionality. With SIPI, you don't, as a B2B UA, you don't have to pipe audio through it. It's a SIP engine, basically. But what it does let you do is it lets you modify your SIP headers as a B2B UA provides. So, for instance, if you've got a from field that comes in and it's not E164 and you want your core to be E164, it would give you the ability to change that signaling so that when the SIP hits your core, the SIP invite hits your core, it's E164.
So we probably have time for one more. You had a question? Yeah, I was sorry, I wasn't trying to ignore you, I was just trying to give everyone, but if, yeah.
So on the Calico, you said these are BGP. So I don't want to deal with the complexity of BGP because my hosting provider, they give me two places and I really use my load balancer for doing this kind of timeline. So would you still use Calico or
Well,
without a BGP?
in my humble opinion, I think BGP is pretty simple, relatively speaking. You know, when we talk about BGP, the reality is BGP runs the internet. So, you know, when we talk about scalability, reliability, and things of that nature, it's a pretty proven protocol. I mean, I think it's fair to say that, you know, it's pretty solid. And so, you know, that being the case, and as widespread support there is for BGP, from an implementation standpoint, I think I would still use Calico. In a cloud environment, there are a lot of alternatives to physical routers, if you will. There's ViOS, there's a lot of, you know, Cisco, iOS XM, if you're interested in that. There's a lot of alternatives that you can use there.
Cool. So I think we'll wrap it up there, just, you know, make sure that we have time for everyone else to get in, so.
We have a swag table, help yourself. There's t-shirts, cups, stickers. Knock yourselves out. Appreciate it.
Thanks a lot.